In this paper, we propose a pipeline for automatically generating safety-critical traffic scenarios. Safety validation of motion planning algorithms requires a large amount of traffic data for testing. One of the commonly practiced approach is to conduct real test drives. While it provides us with realistic data, it is often overly expensive and time-consuming. Data from recorded real-world traffic can be further used to test motion planning algorithms in simulation. However, many publicly available datasets only feature a comparatively small number of maps and scenarios. Also, it is intrinsically difficult to scale up due to the large effort required in creating such datasets. The goal of our approach is to provide a virtual pipeline for automatically generating challenging and safety-critical test scenarios. Our approach addresses the following problems. Firstly, how to obtain diverse road networks. Some of the features of a road network include topology, geometry, the number of lanes, and the number of crossing lanes. The figure shows examples of different road networks. Secondly, how to efficiently obtain safety-critical traffic scenarios. One reason why the validation of automated vehicles requires a lot of data is that safety-critical scenarios occur rarely. When using traffic simulation, the data collection can be achieved more easily. However, those simulators usually only aim for safe traffic behaviors. In this paper, we show how traffic simulators can still be used to generate safety-critical scenarios. Before diving into our pipeline, we will first introduce the utilized software platforms. The generated scenarios are presented in common road format. Common road networks are in turn represented in lanelet format. An example of lanelets can be seen in the figure. A lanelet is described by its left and right bounds and thus provides a detailed road representation. To generate a large variety of lanelet maps automatically, we use the geographic information provided by OpenStreetMap as the input. Since OpenStreetMap uses a high-level map representation, which doesn't provide the required level of detail for automated driving, we have created a converter to bridge this gap. Lastly, in the process of scenario generation, we use the traffic simulator Sumo, which is capable of handling even large and complex road networks. Our pipeline for scenario generation is a three-step approach, which includes the following steps. Step 1. Extracting intersections from OpenStreetMap by using our Globetrotter tool. In this step, the geographic database GeoNames helps us to allocate candidate regions for intersection extraction. After converting the candidate regions into their lanelet format, we select and keep the most interesting intersections. In step 2, we generate scenarios by populating the intersections using the Sumo traffic simulator. Since the obtained scenarios are in general not safety critical, we optimize them in step 3 with respect to a criticality criterion. Thus, in the end we obtain safety critical traffic scenarios on a diverse set of road networks. Let's start with explaining the workflow of Globetrotter. As mentioned, it takes the OpenStreetMap data as input and outputs common road networks. The major steps of Globetrotter include retrieving candidate regions, extracting intersections, and selecting interesting intersections. As the road networks across the globe are mostly concentrated at populated regions, randomly sampling the Earth's surface is not a very efficient way to retrieve candidate regions for road network extraction. For this reason, we use GeoNames geographic data to help us allocate populated candidate regions. Retrieved regions are converted into lanelet networks. An example of the converted map is shown in the figure. To obtain all intersections in a given road network, we first extract all forking points therein, which are shown with gray circles in the figure. We then apply the hierarchical agglomerative clustering algorithm to the forking points. The advantage of this algorithm is that, Instead of specifying the exact number of clusters beforehand, we only need to specify the minimum distance between each pair of clusters. In the figure, the dendrogram of the clustering result is shown, with the distance threshold set to 35 meters. We enclose all forking points within a cluster with a minimum circle, and expand the circle with a radius margin. Finally, it is cut out as an intersection. Out of the tens of thousands generated intersections, we only wish to keep those that are particularly interesting or unique with respect to their features. These include the number of lanelets, forking points, and the number of crossing lanelets. This can be seen as a multivariate outlier detection problem. The basic idea behind is that we take the rarely occurring outliers as unique intersections. To tackle this outlier detection problem, we adopt the isolation forest algorithm. This is because it is unsupervised, capable of handling multiple dimensions of features, as well as only requires a limited effort of hand-tuning its parameters. We have applied Globetrotter to several cities across Europe, as indicated by the small blue dots. On the right side, we present a selection of diverse intersections generated by Globetrotter. Next, we generate test scenarios for motion planning algorithms on the extracted maps. Our scenarios are defined by an initial state, from which a feasible trajectory has to be found by the motion planner. This trajectory needs to avoid obstacles and stay on the permissible road surface. We will create critical scenarios by optimizing the initially uncritical ones. To obtain the initial scenario candidates, we use the traffic simulator SUMO to populate the maps with traffic participants. From the simulated trajectories, we select vehicles that encounter interesting situations to obtain the initial state for the planning problem of our scenarios. Please note that these vehicles do not necessarily need to encounter safety-critical scenarios, since the subsequent optimization process will take care of this. For example, we select vehicles that pass interesting locations on the map, such as the entrance of intersections, the diverging lanes, and the merging lanes. Furthermore, we select vehicles which perform certain maneuvers, such as overtaking, taking a turn, or changing lanes. From each of the selected vehicles, we create a planning problem for a motion planner by saving its initial state. Subsequently, we optimize the trajectories of the surrounding vehicles with respect to a criticality metric. This metric is computed using the drivable area. The drivable area is the projection of the reachable set of the vehicle to the position domain. Thus, it is the set of all feasible trajectories which avoid obstacles or forbidden areas on the road. During scenario optimization, we use the size of the drivable area over time as the criticality metric, since a small drivable area implies that only a small set of possible solutions to the planning problem exist. Thanks to this metric, our scenarios can be generated independent of a specific motion planner. We define a critical area profile and penalize deviations from it in the cost function of the optimization. As additional constraints, we require that all optimized trajectories of other vehicles remain collision-free. The parameterization and handling of constraints is explained in detail in our paper. Next, we show results from the optimization of more than 1,400 scenarios. In the left plot, we show the size of the drivable area over time for the initial and optimized scenario, which is averaged over all scenarios. In the histogram on the right, we show the ratio of the size of the final drivable area to that of the pre-optimized one. Both plots show that our algorithm effectively reduces the solution space in the majority of the scenarios. Let us now have a look at some concrete scenarios before and after the optimization. At the initial time step, we show the selected ego vehicle. In the following time steps, we show its drivable area. In the initial scenario obtained from SUMO, the vehicle can freely pass through the intersection without evading other vehicles. In the optimized scenario, the ego vehicle needs to avoid a bike coming from the left, which was introduced by our optimizer. Additionally, it is not possible anymore to drive straight due to a turning vehicle. Using our approach, we created a diverse dataset of challenging and safety-critical scenarios. The following examples from this dataset demonstrate that our approach is able to generate critical scenarios, where the motion planner has to perform immediate action to avoid a collision. Since we compute a drivable area, it is ensured that there always exists a safe solution which the motion planner can find. To conclude, our pipeline is able to automatically extract interesting road networks across the globe and to generate diverse, challenging, and safety-critical traffic scenarios. All scenarios are available as part of the Common Road Benchmark. Thank you for watching.